today's class, let's go ahead in talking about little more in detail about what are the different tests that we'll come across in the lab for determining the shear strength of the soil. So why I'm talking about different tests means why not a single test that is sufficient means some particular tests or some particular equipment which we are going to be using has got certain limitations for some kind of soils only, and some other tests which we are going to be talking about are more effective in some conditions of the soil. So depending on your requirement, what you are looking at, or depending on the condition of the soil, what you are looking at, we can go ahead in determining the shear strength of the soil for that particular condition of the soil. So we'll continue our discussion with this. In the last class, we were trying to talk about in case if I know the state of stress acting on the soil sample in terms of the total stresses, then we said we can go on to define your failure envelope, or we can go on to construct your failure envelope for the total state of stresses corresponding to different soil samples what we are testing. And in case if it is in terms of effective state of stresses also, we can go on to construct your Mohr circles and we can define your failure envelope. Then that subsequent failure envelopes, whatever we are going to be getting for representing total stress, will give you C5 parameters of that soil, and for represented effective stress data, then it will give you what is called as C dash and phi dash parameters, where C and phi parameters are called as your shear strength parameters for considered total stress data, and C dash phi dash is nothing but once again we call them as shear strength parameters only, but for considered effective stress data. Okay, let's say if I just want to understand what could be the relation between your major principal stress and minor principal stress, that's nothing but your stress acting on horizontal plane, which is in the vertical direction, and the stress acting on your vertical plane, which is nothing but in the horizontal direction. So if I just want to understand at the failure of that soil sample, if I want to understand the relation between the state of stress acting on the soil sample, if stress acting on the soil sample in horizontal direction is known, then how to calculate the amount of stress that was required to cause the failure in your soil sample in vertical direction, or vice versa. That means if stress that is getting applied on the soil sample in vertical direction, if it is known, then how much could be the stress in the horizontal direction that is to be applied on the soil to cause the failure in the soil. Okay, so either of the way we can try to talk about it, and that calculation also, that discussion also we can try to talk in terms of your effective stress data or in terms of your total stress data. If I am trying to talk in terms of your effective stress data, I'll have the relationship between sigma 1 dash and sigma 3 dash. In case if I am talking in terms of total stress data, then I'll have a relationship between sigma 1 and sigma 3. So if sigma 1 at failure is known, I can calculate sigma 3 at failure, or if sigma 3 at failure is known, I can try to calculate here sigma 1 at failure, given or knowing what are the C5 parameters of that particular soil. If I know the C5 parameters of the soil, given either your horizontal stress or vertical stress, what your soil is experiencing, then the other stress we can try to calculate. Okay, so either with respect to total stress condition or with respect to your effective stress condition. Okay, so we'll just try to look at how to get that relation, what we were trying to talk about. Let's say I am considering the effective stress data. In terms of the effective stress data, I have constructed Mohr circle. So similar Mohr circles, if I am constructing, I'll get a failure envelope as like what is represented here. Okay, so if I'm further extending that failure envelope beyond the intercept what it is making with the vertical axis, so somewhere that failure envelope is going to be meeting your horizontal axis. Let's say this point where your failure envelope is meeting your horizontal axis, let me represent it as some point A, and this point where the failure envelope is intersecting your vertical axis, this point let me call it as some point B, and this origin is what I am representing it as, let's say, point D. Okay, yeah, so the point where we are indicating that no, your failure envelope is represented as a tangent to your Mohr circle. So that point where your Mohr circle and failure envelope is touching each other, I am indicating with your notation, let's say F, and the center of the Mohr circle I am indicating with the notation E. Okay, so I'm just trying to talk about some mathematical construction, nothing more than that. So if I'm trying to look at Okay, so I'll be just trying to look at some. I'll be just looking at your triangle. Let's say AFE. So when I say AFE, it means this triangle with right angle at point F. And the angle what is getting formed at point A is nothing but it is your phi dash angle, obviously, because it's the slope of your failure envelope is what we write it as phi dash. And we said that the failure envelope is tangential to your Mohr circle. So from the center of the Mohr circle, if we are trying to represent your line to the tangential point, this line is going to be perpendicular. So this means at point F, the angle what is formed is 90 degrees. Then automatically this remaining angle is what I can write it as 90 minus phi dash. Okay. So in the triangle AFE, which I am trying to look at. So ultimately I just want to develop a relationship between what is called as sigma 1 dash and sigma 3 dash with respect to the failure condition of the soil sample. So let me write down what is sine phi dash is equal to from this triangle AFE with the right angle position at F. So if I start writing down what is sine phi dash is nothing but opposite side is going to be your EF and the hypotenuse is going to be your A to E distance. Now what is EF indicating? EF distance is indicating you the radius of the Mohr circle. So how do we write down the radius of the Mohr circle? Sigma 1 dash minus sigma 3 dash by 2 indicates your radius of the Mohr circle. This total divided by AE. AE distance is what? AE distance is nothing but AD distance plus D2E distance. AD plus D2E. What is AD distance equal to? This AD distance, how are we getting? So this AD distance I am getting from your triangle ADB. Okay. So from the triangle, if I am looking at from triangle ADB, if I say opposite side is C dash is what I know. Okay. Adjacent side is what I wanted to calculate. So I can say tan phi dash is equal to BD by AD. From this I can say AD is nothing but BD by tan phi dash. So which either wise I can also write it as BD into cot phi dash, because 1 by tan phi dash is what I can also write it as your cot phi dash. So that's how we are getting your distance AD. Now what is the distance from D to E point? Distance from E to D to E. So D point is representing the origin of that particular coordinate system. And E point is representing your center of your Mohr circle. So from the origin, at what distance the center of the Mohr circle would exist? At distance nothing but sigma 1 dash plus sigma 3 dash by 2. So AD distance is known, DE distance is known. So I can go on to substitute into this particular expression. Okay. So if I try to substitute that particular data into this expression, what I will be getting is this, that what I will be getting. Okay. So in the process of substituting the data of AD is equal to BD cot phi dash, and what is your BD? BD is nothing but C dash. Okay. So AD is ultimately what I am writing it as C dash into cot phi dash. And how about DE? DE is nothing but your sigma 1 dash plus sigma 3 dash by 2. Okay. So AD data is known, DE data is known. I can go back to substitute into this particular expression, that is nothing but sine phi dash is equal to sigma 1 dash minus sigma 3 dash by 2 total divided by AD plus DE. That AD plus DE term what I have is what I am taking onto the left side. So in the process, if I am taking it onto the left side, what I'll have is sine phi dash into AD is C dash cot phi dash plus DE is sigma 1 dash plus sigma 3 dash by 2. Okay. So I am skipping all those terms and I am directly writing those that particular expression here. Okay. So the first expression what I have in this page. Now in the process, I just want to separate out your terms of sigma 1 dash onto one side and sigma 3 dash onto one side, so that if sigma 3 dash data is known, I can calculate sigma 1 dash. If sigma 1 dash data is known, I can calculate your sigma 3 dash. So in the process, I'm just trying to segregate all your terms. Please look at your mathematical expression, how they are solved. And ultimately, when you are trying to segregate all your terms of sigma 1 dash onto one side and sigma 3 dash onto the other side, this is how I'll be getting a relation. Okay, so sigma 1 dash is equal to sigma 3 dash into 1 plus sine phi dash by 1 minus sine phi dash plus 2c dash into cos phi dash by 1 minus sine phi dash. This is what I have as a relation between sigma 1 dash and sigma 3 dash. In case if sigma 3 dash data is known, I can calculate sigma 1 dash at failure of that soil sample. Or if sigma 1 dash data is known, then I can go ahead in calculating your sigma 3 dash at failure of the soil sample, given C5 parameters of that particular soil. Okay, so if I know the C5 parameters of that particular soil, and if I know how much is my stress condition, at least which is acting on one principal plane, then I can go ahead in calculating your stress acting on the other principal plane at failure condition of that particular soil. At the failure of the soil, how much could be the stress that would be acting on the other principal plane. So in the process of rewriting your terms in simplest form, if you will be looking into the literature, you will be finding it as sigma 1 dash is equal to sigma 3 dash into n phi or n phi dash plus 2c dash into under root of n phi. Okay, so this n phi is basically what we can write is n phi is what we can write it as 1 plus sine phi dash by 1 minus sine phi dash. So this 1 plus sine phi dash by 1 minus sine phi dash, if we try to simplify it, we'll also be getting it like this: tan square 45 plus phi dash by 2. In case if I have the relation like 1 minus sine phi dash by 1 plus sine phi dash, then in terms of tan square, it comes out to be tan square 45 minus phi dash by 2. So from trigonometry is what we are writing it, rewriting that particular process. Okay, so I can go ahead in writing your expression like this. So if I know how much is my major principal stress acting on the soil sample, I can calculate my minor principal stress. Or if I know my minor principal stress acting on the soil sample, I can go ahead in calculating my major principal stress that was required to cause the failure in your soil sample. Now moving on, how do we determine the so-called shear strength parameters of the soil? That's nothing but C5 parameters in terms of total stress condition, if I am looking at, or C dash phi dash parameters in terms of your effective stress parameters, effective state of stress acting on the soil, if I am looking at. So ultimately, my objective is to understand how to know the so-called properties of the soil for determining the shear strength of that particular soil. So for determining the shear strength of a particular soil, what properties of the soil that we'll be requiring is here shear strength properties of the soil. So what are those shear strength properties of the soil that we are talking about? It's either C5 parameters or C dash phi dash parameters. So C5 parameters I'll be getting from the failure envelope defined with respect to total stress condition acting on the soil, or C dash phi dash I'll be getting from your failure envelope what is defined in the case of your effective stress data represented which is acting on your soil. Okay. So let's look at some of those different tests from which we can try to determine your C5 parameters or C dash phi dash parameters for a given soil. So we have broadly some lab tests and some field tests by which we can try to determine the shear strength parameters of the soil. And some of those lab tests what we will be coming across as of this course is concerned are listed here in red. So that's direct shear test is what we will be trying to talk about. Unconfined compression test is one of the tests which we'll be trying to talk about. And we have different types of triaxial tests which we'll be trying to talk about. I'll try to introduce one by one in our subsequent classes. And we'll also be coming across with another type of shear test, that is here laboratory vane shear test in the case of your lab. And various other tests are also there, but we'll not be coming across as of our basic fundamental course is concerned. I cannot use whatever test I want on any type of soil. So you'll have some limitations for some particular type of test only to be used on for particular type of soils. Okay. So depending on your type of soil depending on the test condition which you want to simulate it with field. Then we'll go on to talk about that particular type of test, so that we try to get exact condition of the ground, what is there in the field, exact condition of the properties of the soil which are existing in the field in undisturbed state. And likewise, we also come across with different other field tests which will also be looking at. Okay, but these field tests, whatever are listed here, like static cone penetration test and standard penetration test and vein shear test. So these tests we'll be trying to talk about in next course, that is foundation engineering course. Okay, some of those tests which are listed under field test. Okay, so even from lab tests I can determine your C5 parameters. Even from field tests also we can try to determine your C5 parameters of the soil. But lab tests will help us in directly determining the C5 parameters, whereas your field test will not directly give you the C5 parameters of the soil. Rather, they would give some data with respect to that particular test, and we have different empirical relations, correlations which are available with respect to the data what is determined from that field test to get your corresponding C5 parameters of that soil what we are looking at. Okay, so in the lab we can directly determine your C5 parameters of that exact soil in its exact condition. So now, as of this course is concerned, our objective is to look at all these lab tests what we have listed here, 4 lab tests, 4 categories of lab tests. Okay, so which we'll be looking in this particular unit, that is under the shear strength of the soils. So let's say this is how in general the condition of the soil what we have in the field. Okay, so I'm just trying to say, I'm considering if I want to determine the shear strength parameters of that particular soil what is there in the field. So what I'll do is, I'll not be taking the complete soil from the field, rather I'll be taking a representative soil sample. Representative soil sample means the soil sample which is collected from the field represents the original condition of the soil what is existing in the field. Okay, so it's a kind of a representative sample which is representing the complete soil which is there in the field. Okay, so with the help of that particular representative sample, let's say representative sample means it's a soil sample what I am trying to collect from the field in undisturbed state. Okay, so you might have some state of stresses acting on that particular soil sample. Now what is going to happen? This is all before the construction of the structure. Now during the construction or after the construction of the structure, what is going to happen in terms of the stresses acting on this soil element what I am looking at, or the representative soil what I am looking at? So you are going to come across with increase in stresses in the soil. Okay, so in some kind of geotechnical problems, we see that increment in stress comes in the form of vertical direction. In some other kind of geotechnical engineering structures, we come across with increment in stress in the horizontal direction. Due to foundation, due to any other superstructural load, increment in stress would come in the vertical direction. But because of, let's say, your retaining wall, okay, so due to the case of the retaining wall, what we see is that your increment in stress comes not in the vertical direction of the soil, rather in the lateral direction, that is in the horizontal direction of the soil sample, you would come across with the increment in stress getting applied. Okay, so why is it all that? We'll try to talk in the foundation engineering course first unit, where we'll try to talk about your earth pressure in the soil. Okay, so we'll try to introduce there. Why is that in the lateral direction you have increment in stress? But for now, in majority of the cases, in general, what we see is the so-called increment in stress coming in your soil would be because of your superstructure or because of various things. So which generally comes in your vertical direction. Now, due to that increment in stress in the vertical direction, what is going to happen in the soil is what we need to understand. Now, what could be that maximum increment in stress that you can try to induce in that particular soil before it is said to be undergoing the failure? So if I want to understand what could be that maximum stress that I can try to transfer onto that soil in the form of superstructural load or in the form of any other additional load, so for knowing that, I should be knowing the C5 parameters of that soil. Okay, so for knowing C5 parameters, I have to construct your or I have to define what is called as the failure envelope. So for defining the failure envelope, you have to have minimally of 3 soil samples tested under different loading conditions. Under different loading conditions, how is the behavior of the soil is what we'll try to understand, and then according to that, we'll try to define what is called as a failure envelope. From that failure envelope, we'll define your C5 parameters. If I know the C5 parameters, by making use of the C5 parameters, then I can go on to understand how much stress increment I can try to allow onto that particular soil, okay, before it is said to be undergoing the failure. So when the soil sample is taken out from the ground, then the amount of stresses what gets applied on the soil sample obviously gets released, because once the soil is taken out from the ground from certain depth, so whatever stresses that were getting applied on that soil when it was inside the ground, so that stresses gets released when you take out the soil sample out. And in order to simulate the same condition, in order to incorporate the same condition of the stresses what your soil sample has been experiencing when it was there in the field, so we go on to apply what is called as your vertical stress on the soil sample and horizontal stress on the soil sample. And when it comes to the case of your triaxial test, because broadly here I am looking at 2 categories of tests, your triaxial test and the other category of test is your direct shear test. So in the case of your direct shear test, the intensity of vertical stress that is getting applied on the soil sample is kept constant. But what we are trying to do is, we are trying to increase the loading in the horizontal direction on your soil sample to cause the shearing in the soil sample in the lateral direction. Shearing is what we are trying to introduce in your direct shear test forcefully in the horizontal direction. But whereas in the case of your triaxial test, what we do is, the amount of horizontal stress that gets applied on the soil sample is kept constant throughout the test. But in which direction we are trying to increase the stress on the soil sample to cause the shearing in the soil means it is the increase in stress levels in the vertical direction. So in the vertical direction, we keep on increasing the stresses acting on the soil, and at some amount of stress increment in the vertical direction, we are going to see the failure happening in the soil. Okay. So what we do is, first we take the representative soil sample from the site for which I want to determine the C5 parameters. Then first step what we try to do is, we try to simulate the same field condition in the lab. Simulating the same field condition in the lab means, I might have taken the soil sample from certain depth below the ground. So initially when the soil sample was there at that particular depth below the ground, it might have been subjected to some normal stress in horizontal direction, some normal stress in the vertical direction. So I am just trying to replicate the condition of that stress on my soil sample. That is what we call it as your initial stress condition. Next, in order to cause the shearing in the soil sample, accordingly, I am going to increase the loading on the soil sample. In the case of direct shear test, we go on to increase the loading in the horizontal direction on the soil sample. And whereas in the case of your triaxial test, we go on to increase the loading on the soil sample in the vertical direction. So ultimately, to see that the failure gets initiated in the soil. Once the failure is getting initiated in the soil, then what we look at is, how much was that increment in stress that your soil sample is subjected to, because of which the failure is taking place in the soil. Okay, I repeat, because of how much increment in stress that is getting applied on the soil, your soil is undergoing the failure. That is what ultimate objective, what we are going to be looking at for each of the soil sample that we are going to be testing in the lab. So to start with, first we'll start talking with respect to your direct shear test. Once we discuss with regard to the direct shear test, how to determine the C5 parameters, then we'll move on with the other laboratory tests, like it could be your unconfined compression tests, or your triaxial tests, or maybe your vane shear test. Okay. So let us look at the schematic diagram of your direct shear test setup. Okay. So you have what is called as the direct shear test setup, in which the main core part of this direct shear test setup is your direct shear box. Okay. So this complete what is indicated here is what is called as your direct shear box. Okay. With some additional accessories represented here, proving ring, dial gauges, loading frame, and so on. But to be more specific, this is exactly to be, if I need to be talking about, this is your direct shear box. Okay, so now what is that we are looking at in the case of this direct shear box? So now what does this direct shear test setup contain? What is that or how are we trying to perform the test in the case of this direct shear test? So in this direct shear test setup, this exactly whatever you could see here is what we call it as your direct shear box. In the direct shear box, what do you have means? Okay, let's now understand it. Inside the direct shear box, what is that exactly we are going to be placing? So we are going to have what is called as two split half portions of square cross sectional pieces of the box, which looks like this in this picture, whatever you could see here. This is your top portion of the split half, and this is the bottom portion of your top split half of that direct shear box. Okay, so what is that ultimately we are trying to do? The top split half portion and the bottom split half portion both are connected to each other. I'm just trying to connect both of them together only. Okay, so top box and it's a hollow cross sectional box. Typically you can look at them here. Okay, so these are those two individual pieces what I am looking at. One will be placed over the other, and on bottom of it you have some proper construction that we have to be taking care of. Okay, so what does that properly I have to take care of it means? So at the bottom of it I have to place what is called as a porous stone. Once again similar kind of discussions. Okay, so here you can see I'll have what is called as a porous stone. On top of the porous stone you will have what is a filter paper, and above that filter paper you will be placing your soil sample, and once again the repetition of the same thing. So on top of the soil sample again you will be placing a filter paper. Above that filter paper you have a porous stone. On top of that porous stone you have a kind of a steel plate with some grooves. Okay, so in between that grooves you will have some small opening to that plate. So whatever the water which comes out of the soil passes through your porous stone, and from the porous stone whatever water particles that comes out gets drained out of this particular plate, which is immediately there above your porous stone. Okay, so to that particular plate we are going to have some small openings, so that through that small opening, in case if the drainage is happening through that particular soil what I am using in the test, okay, so that water can easily get drained out of your soil while the shearing process is taking place. Because while you start shearing the soil sample, what is going to happen? Excess pore water pressures will start building up in your soil sample, and due to that excess pore water pressures what are building up in your soil sample, you would see that water particles would try to go out of your interconnected void path and get drained out of your soil. So in the process, if the water particle is trying to get drained out of the soil, so you should have a provision of providing the proper drainage to happen through your soil sample. Okay, so when does the drainage takes place? When you are applying some stresses on the soil. Now how do we apply the stresses on the soil sample? Now here in the case of this direct shear box or direct shear test, look at here. Now above the steel plate, what is there immediately on top of your porous stone? You have what is called as a pressure pad. It's a steel plate once again with a kind of an impression, undulated profile like this. This is how that particular plate would look like, with some undulated impression. Now inside this undulated impression, we are going to have a steel ball which is going to be placed. On top of this steel ball, you'll have a loading frame which is going to be coming. And what does that loading frame does means? It tries to transfer the load on your soil. Okay, so you're ultimately the loading frame, what is it doing means? It is trying to transfer the loading onto your soil sample. So how is that loading coming? From the loading frame onto the loading frame, we'll be adding some loads. So load which is getting applied onto the loading frame gets transferred onto the top of the soil sample, and that load we call it as your normal load, and it's a point load basically. So why? Because it is called as a point load means this so-called point of contact with the steel ball and this plate is going to be a point contact. So once the load what is getting applied through this ball onto the plate is considered as your point load. So this particular steel plate will ensure that whatever the point load that was getting applied will more or less uniformly distribute that loading from the bottom of that plate. So more or less it uniformly distributes the loading onto the next portion of the steel plate what is placed, which is used for the purpose of drainage or initiating the shearing between the soil. Okay. So below this, now from this steel pad, you can have that more or less the pressure is further uniformly getting spreaded, and from this plate you have your porous stone. So further proper uniform distribution of load is happening onto the porous stone from its top plate, and from the porous stone the load is getting distributed onto your soil sample. Okay, this is top half of your hollow cross sectional box, and above below which you have the other half of your hollow cross sectional square split box, and in this completely you have your soil. Now what is happening, whatever the load that is coming from your top porous stone is uniformly assumed to be spreading on the complete area of your soil. So that's how we say we are inducing what is called as a normal stress on your soil sample. Now how is this direct shear test performed? So what we start doing is, initially we start applying some intensity of normal stress on the soil, and for that applied intensity of normal stress on the soil sample, mostly in the lab whenever we talk about, let's say we start with a normal stress which is equal to 0.5 kg per centimeter square. For that amount of normal stress what was applied on the soil sample, we start inducing what is called as a horizontal displacement in the bottom split half portion of your direct shear box. And due to that horizontal displacement, what you are trying to induce in your soil, so you are going to see some amount of resistance what is being offered at that split half portion. If you can look at the soil sample here, this is the region of your split half. Okay, so where is the soil going to undergo the failure means this bottom split half portion of the box is undergoing the displacement in this rightward direction, whereas the top split half portion of the box will remain at this position itself, because you have a proving ring. When the top split half portion which is sitting on the bottom split half, if the bottom split half is trying to move, top split half also tries to move, but this so-called reaction frame whatever we have here, okay, so this reaction frame will not allow your top split half portion of your direct shear box to undergo the displacement. So it is opposing the motion in your top split half portion of the direct shear box. So how much was that reaction which was offered by that reaction frame on the top split half portion of the direct shear box is what we consider as your force which is getting applied tangential to the surface of contact of top split half portion of the soil to that of the bottom split half portion of the soil, about which your shearing is happening between the grains, soil grains. Okay, so once I know how much is that force being resisted at this surface of shearing between soil there in the top split half portion and soil which is there in the bottom split half portion. So if I want to understand that amount of shearing resistance, so we have what is called as a proving ring. Okay, so this is what we call it as proving ring. So this proving ring is going to read how much is that reaction going to be offered at that surface of contact where the shearing is getting initiated in the soil. Okay, so that force what is being read from your proving ring is what we call it as your shear force, which is getting developed tangential to the surface of contact about which the failure is happening. So at this surface of contact while the shearing is happening, how much was the resisting force against the failure is what we are trying to understand. Now once the force is known, over what cross sectional area that particular force is getting developed. Okay, so what we roughly assume is the cross sectional area over which that particular shear force is getting developed while the displacement is happening in your relative displacement is happening between top split half portion of the box and the bottom split half portion of the box. So roughly we assume that the force is getting developed over the complete cross sectional area of this particular surface of contact. That corresponding cross sectional area of the surface of contact is nothing but the cross sectional area of your split half box into which your soil sample is placed, which is nothing but we call it as 6 centimeter by 6 centimeter cross sectional area is the cross sectional area of the box into which the soil sample is placed. And the height of that soil sample which is getting placed into that split half box is only 2 centimeters. Okay, so 2 centimeters in the sense, first 1 centimeter, that's the top 1 centimeter of soil layer will be in the top split half region of the box. Next 1 centimeter thickness of the soil sample is going to be there in the bottom split half portion of your direct shear box. Okay, so this is a clear picture about how each and every individual part of the direct shear box will be looking at. Okay, so we have to arrange your direct shear box in a systematic manner, starting from the bottom. So from the at the bottom, you'll have a plate which will be acting like the base for that complete setup. So on top of that plate, you'll be placing a porous stone. On top of that porous stone, you'll be placing a filter paper. On top of that filter paper, you'll be placing your soil sample. Okay, so in case if you are trying to talk about conducting the direct shear test on cohesive soil, then you can push this split half portion of the direct shear cross-sectional, hollow cross-sectional box, whatever I said, of cross-section 6 centimeter by 6 centimeter. That itself, you can push it into the ground from whichever depth you want to collect the soil sample. Take it and exactly place that soil sample into that hollow region of that particular box. Once the soil sample is placed, no, I am not interested in cohesive soil like clay soil for which I want to conduct my direct shear test. Let's say if it is for sandy soil for which I am looking at, determine the C5 parameters based on your direct shear test. Then take that sandy soil. According to that particular field density at which that soil is there, so say at same density, you are required to place that particular soil into that direct shear box. Okay. Once the soil sample is placed into that direct shear box, into that hollow cross-sectional region, you can make use of a plate to properly level the surface of that soil, which is placed into this container. Look at here. So once the soil is placed, try to level the surface of that particular soil so that whatever load that comes from the top can be uniformly spread over the complete cross-sectional area of the soil. And once the soil is properly leveled, on top of it, you will place your porous stone. On top of that porous stone, you will place a plate of this type, whatever I was trying to talk about. On top of this plate, you are going to have this one. Okay, so which is nothing but this one, pressure pad, whatever I have earlier told. So on top of that pressure pad, you are going to have a kind of a steel ball. You can look at here. So load from the loading frame gets applied in the vertical direction directly on top of that steel ball. So from the steel ball onto the pressure pad, it gets uniformly distributed. Pressure plate, I can say. From the pressure plate, you have a steel plate which is useful for allowing the drainage. So onto that steel plate, load distribution happens. Next, from that steel plate, load distribution further happens onto your porous stone. From the porous stone, load distribution further uniformly assumed to be getting or assumed to have a uniform further distribution of the load onto your soil sample. Okay, that's how you apply some normal stress on your soil sample, which is assumed to be uniform over the complete cross-sectional area of the soil sample. Once we say my soil sample is properly placed in that direct shear box, then we take that complete setup of the direct shear box and place this particular complete setup of the direct shear box inside your direct shear test setup. Okay, this is whatever the picture, schematic picture that we are able to see here is what we call it as your direct shear test setup. And inside this direct shear test setup, this is the region where we are going to be placing your direct shear box. Look at the region what I am trying to mark. Okay, so in this particular region, we are going to be placing your direct shear box. On top of the direct shear box, I said through a loading frame, you could see this is my loading frame. So through the loading frame, we are going to apply what is called as your vertical loads onto the soil sample. So you will have some circular loading discs which are going to be hanged to it, to the loading frame at the bottom. So from that circular loading disc, whatever you have applied, load gets transferred through this vertical member and ultimately gets applied onto your direct shear box through the contact of this loading frame, which the loading frame is making with your steel ball, which is immediately there on top of your pressure plate. Okay, so from the loading frame, load gets transferred onto that steel ball. From that steel ball onto the next. Ultimately, a uniform pressure distribution is assumed to be getting applied in the vertical direction on the soil sample. Okay, so once the normal stress is applied on the soil sample, then our next job is to cause a constant rate of displacement in the bottom split half portion. Let's say this is my top split half, this is the bottom split half. So on the bottom split half portion, I am trying to push this bottom split half portion of the direct shear box at a constant rate of displacement. Okay, so if you look at here, you have a motorized mechanism in your direct shear test setup. Okay, now what does this motorized mechanism does means you have different conditions in this motorized mechanism where you can try to introduce different strains at which you can try to cause the shearing in the soil sample. The rate of displacement at which you want to cause the shearing in the soil sample, you can have a control on it. If I want to cause the shearing relatively at a faster rate, then I can introduce the strain rate to be relatively higher. So how do we define strain? Displacement. How much amount of displacement that you want to introduce in that particular soil at a regular interval of time. Let's say, for example, if I set a strain rate of 0.01 mm per minute. So what does it mean? For every 1 minute, I should have a shearing or a relative shearing happening in my soil, which is equal to 0.01 mm. Now, for that amount of relative shearing of 0.01 mm, or in order to have a relative displacement of your bottom split half portion of the box, which is 0.01 mm per minute, in order to have that much amount of displacement, what should be the corresponding reaction that is to be offered by the reaction frame? Whatever you could see here is nothing but we call it as the reaction frame, this portion. Okay, so for ensuring that amount of constant deformation happens in the soil to undergo the failure at the surface of contact between the soil of top split half and the soil of the bottom split half. So how much was the subsequent reaction that is to be getting developed on the soil will be understood by reading the data from your proving ring, whatever is provided here. And in the process of the complete test, you are going to have even dial gauges which are fitted to your test setup. Okay, so you could see one dial gauge fitted in the vertical direction. You could see another dial gauge fitted in the horizontal direction. Okay, so the vertical dial gauge, whatever is placed, is useful for measuring the vertical deformation happening in the soil due to the applied loading in the vertical direction, and also during the process of shearing, how is the height of the soil sample varying. Okay, and this horizontal dial gauge which is placed in the horizontal direction. So what is the use of that dial gauge which is placed in the horizontal direction means that dial gauge. Okay, so this is that dial gauge what I am trying to talk about, which is placed for measuring the deformations of your soil in the horizontal direction. Because we said we are going to trying to introduce what is called as the constant rate of displacement to happen in your direct shear box in the bottom split half portion. So how much is that displacement that you are having in your direct shear box at regular interval of time? Okay, so if I want to measure, then with the help of this dial gauge which is placed in the horizontal direction, I can try to look at it. Okay, so depending on the amount of displacement happening, then the corresponding amount of reaction what was getting developed is read from your proving ring. So ultimately, what is that we are going to be finding out from this test? We are applying some normal loading on the soil sample, from which we get how much is the amount of normal stress that was getting induced in your soil sample. So how do we get the normal stress? I know how much was the normal force applied divided by over what cross-sectional area that normal force was getting applied. So over the complete cross-sectional area of the soil sample, the normal force whatever you have applied is getting applied. So it means I know how much was the normal stress that I tried to apply on the soil sample. Okay, so for this applied normal stress, what was the corresponding shear stress that was getting developed in your soil sample at failure? I repeat, at failure. So how much was the maximum shear stress that your soil sample can resist before it is said to be undergoing the failure? Okay, so that is what we are going to be calculating. So how do we calculate that shear stress, maximum shear stress that your soil sample can resist before it is said to be undergoing the failure means? So shear stress, we calculate it as shear force divided by the corresponding cross-sectional area over which that particular shear force is getting developed, the corresponding area over which the shearing is getting developed between top split half portion of the soil and the bottom split half portion of the soil. So soil which is there in the top portion of the box, soil which is there in the bottom portion of the box, they relatively get sheared off, and we see what is that surface of contact between which the shearing is happening between the soil grains. Okay, so at different intervals of time, I can go on to measure how much is your proving ring reading, and that proving ring reading is what is it going to tell you, how much is that shear force getting developed at the surface of contact of failure, and divided by the cross-sectional area of the sample. So for most of the cases, whenever we are trying to talk about the direct shear test, in general, people do consider the cross-sectional area of the soil sample to remain constant. Okay, the contact area what is available, I repeat, the contact area what is available with respect to which the failure is happening, that contact area is assumed to be constant. But however, that area is not exactly constant. Why? What is happening? Let's say this is the top split half portion of the soil box, this is the bottom split half portion of the soil box. And once this bottom split half portion of the soil box is trying to slide due to your horizontal displacement, what you are trying to introduce in it, then what is happening with regard to the surface of contact, whatever we have. So the surface of contact between the soil of the top split half and between the soil of your bottom split half, the surface of contact is decreasing. As you continuously try to cause the displacement, the contact area between the top split half portion of the soil and the bottom split half portion of the soil is decreasing. But most of the times people do not take into consideration of that decreased contact area for estimating your shear stress value. Okay, so they simply consider the constant cross-sectional area to always remain, and by considering the constant cross-sectional area, they calculate. But exactly speaking, while the horizontal displacement is happening in the soil, horizontal shear is happening in between the parts of the soil, then the contact area of your top portion of the soil box, bottom portion of the split half box, the contact area starts getting decreased. Okay, so exactly speaking, if I am required to know how much was the correct cross-sectional area or correct surface of contact, then this is that expression what we can make use of for exactly finding out your correct area of contact what was getting developed about which the shearing is happening. Okay, but however, in most of the cases you don't see this expression used exactly for finding out your correct area. They simply blindly go by what is called as your initial area itself, or the original area itself. So what is that original area? 6 centimeter by 6 centimeter. So this is a sample calculation what is shown here. Okay, so for some amount of normal load what is applied, then we can go on to understand how much is the normal stress, and we start applying, or we try to set some strain rate at which the equipment is going to be operated. Let's say if I am going to set a strain rate of 0.01 mm per minute, so it means that your so-called deformation what you are trying to introduce in your direct shear box, bottom portion of the direct shear box, is 0.01 mm. For every 1 minute, you should have only a deformation in that soil of 0.01 mm. Okay. So at that rate of speed, you are going to cause the shearing in the soil sample, and continuously as the shearing is progressing, we are going to see for corresponding displacement in the soil sample, how much is going to be the amount of shear force what is getting developed based on your proving ring data. And once the proving ring data is known, then we go on to convert that proving ring data into what is called as your shear force value. And once we get the shear force value, we divide that shear force by the area over which that particular shear force is getting developed, and we represent it as your shear stress. Normal stress is known, how much was getting applied on the soil sample, and shear stress is known at different intervals of shearing. Okay, so once we know the shear stress, once we say the shear stress, how much is getting developed in the soil due to the amount of deformation which took place in the soil sample. Let's say this is how your soil in terms of top split half portion and bottom split half portion. As you are trying to introduce the displacement in the bottom split half portion, so due to the displacement of the bottom split half portion of the soil mass, how much was the resistance that is getting developed? So for some amount of displacement introduced, some amount of friction might have got developed. If I know some amount of friction got developed, then corresponding amount of shear stress I can calculate. Some more amount of displacement, some other shear force might have got developed by its area. It gives me some other shear stress. So more displacement that is happening, I'm going to get different shear force values at the surface of contact, which is read from your proving ring, and that different shear forces divided by the area over which that particular shear force is getting developed, it gives me different shear stress data, what I am going to get as this so-called shear deformation is continuously happening in your direct shear soil sample. Now, once we have your test result that we have conducted for one of the soil sample on which you have applied some normal stress, let's say it is something sigma 1, on sample 1, I am talking about once again 3 samples, 3 identical samples only. Okay, soil property is same, soil is same, but only thing is on sample 1 I am applying some normal load or which corresponds to a normal stress which is sigma 1, whereas in the case 2 I am applying some normal stress which is sigma 2. On case 3 I am applying some other normal stress which is sigma 3. Okay, so typically when it comes to the lab, let's say that sigma 1 what we in general talk about is 0.5 kg per centimeter square. Sigma 2 in general what we will be looking at is 1 kg per centimeter square. Sigma 3 what we will be looking at is 1.5 kg per centimeter square. So for these different normal stresses applied on the soil sample, we go on to calculate what could be the maximum shear stress that you will be getting at the failure for sample 1. Similarly, for sample 2, even in the case of your sample 3, at the failure of that soil sample. Okay, so more specifically, let me write it as tau F1. So at the failure of the soil sample, what was that maximum shear stress that you have got corresponding to sample 1, corresponding to sample 2, corresponding to sample 3. So once I have normal stress and its corresponding shear stress, maximum shear stress, what your soil could have resisted before it is said to be undergoing the failure. So normal stress and shear stress data for sample 1 is known. Sample 2, sample 3. Then we have seen in the last class, for 3 soil samples, if I know the corresponding normal stress and shear stress data, then I can go on to plot a graph between normal stress represented on the horizontal axis, shear stress indicated on your vertical axis. Then I'll be getting 3 points, and I'll be just trying to represent a best fitting straight line to pass through those 3 points. Okay, so always we may not have a proper straight line. In case if one data point is here, another data point is here, another data point is here, I cannot draw a straight line passing through all these 3 points like this. It's not correct. So in such case, what I should be doing, if my data points are like this, so I have to see to fit in a best possible straight line. Okay, so in the process of fitting the best possible straight line, so extend that particular straight line, whatever you have, wherever that particular straight line intersects your vertical axis, we call that intercept to be C, and the slope of this is what we represent it as phi. And whereas this line itself, whatever we are indicating, we are calling it as your failure anvil. Okay. Now, what is this top curve? What is this graph? What we have here representing? Let us please try to understand this. When I am talking about sample 1, on that particular sample 1, when some amount of normal stress that is applied, let's say sigma 1 is the normal stress which was applied on my soil sample 1. Now, for that applied intensity of normal stress, when you are trying to cause the shearing in the soil sample, at some amount of shear stress, the soil is said to be undergoing the failure. Okay, so as you keep on increasing the shear displacement in the sense the horizontal displacement in that particular soil sample, as you are trying to continuously cause the shearing in the soil sample in the horizontal direction, the amount of frictional force what is getting developed at this surface of shearing will keep on increases, which is read from your proving ring reading. And from that proving ring divided by the area over which that particular shear force is getting developed, we try to divide it with, and we say the amount of shear stress what is getting developed in the soil for amount of displacement of, let's say, some 1 mm corresponding shear stress developed in the soil is so and so. For an amount of displacement of 10 mm, how much amount of shear stress you are coming across. So for different amount of horizontal displacement happening in your soil sample, so how much is the corresponding shear stresses that are getting developed in the soil is what we'll try to calculate, and we'll try to go ahead in plotting a graph. Okay, so let's say the graph what I am going to be plotting is for shear displacement, or in general I can say horizontal displacement in the soil divided by the corresponding amount of shear stress, how much shear stress is getting developed in that particular soil as you continuously cause the shearing in the soil sample. So what we see is that as the amount of horizontal displacement or the more and more horizontal displacement you are trying to introduce in that particular soil, which is causing the shearing in the soil, you would also see more and more amount of friction gets developed in that particular soil, and at some point of time you might see the curve getting changed like this. What does it indicate? Your shear stress in the soil is continuously increasing, reaching to what is called as some maximum value, and beyond that amount of horizontal displacement, if I further try to cause the shearing in the soil sample more and more, what I could see is that intensity of the shear stress what was getting developed in the soil is continuously decreasing. This could be one pattern of your curve. Okay, this could be one pattern of the curve. In some kind of soils, you could see the pattern of the curve something like this. Now, what is it indicating? The shear stress that is getting developed along that failure surface is continuously increasing. At some amount of displacement, what was getting developed in the soil, for some amount of horizontal displacement getting developed in the soil, we could see that your horizontal stress, what was getting developed, your shear stress, what was getting developed at that along that failure surface was more or less remaining constant. Okay, so even this condition also refers to that of the failure in your soil sample. Now, if you are looking at the condition of your first curve, where should I say, or how do I understand what is my maximum shear stress at which the failure has happened in your soil sample? So what I'll just try to look at is, where is the peak point of your curve? So that peak point of the curve, if I extend it onto your vertical axis, it tells me how much was your maximum shear stress that your soil was capable of holding, or your soil was capable of resisting before it is said to be undergoing the failure. Okay, this is with regard to soil sample, same soil sample, but criteria of failure is as like what is indicated here, 1. In case of sample 2, it's a different type of soil in which you have shear stress continuously increasing, and after some amount of shear displacement or shearing what you caused in the soil, you could see that your shear stress more or less remains constant. So in such case, we try to see what is that maximum shear stress value, and we try to write down, okay, that corresponding maximum shear stress at which the failure is happening in your soil sample. So earlier I said for 3 soil samples, we are going to be plotting a graph between sigma versus tau. So this tau data, what we are indicating exactly is your tau value. That's the shear stress value at the failure of that corresponding soil sample. So for sample 1, when I say I am talking about 3 identical soil samples, okay, before I start talking about this, in which type of soil you will see this pattern of curve 1, in which type of soil you will see this pattern of curve 2. This pattern of curve 1 is generally what we come across in the case of your dense sand or over consolidated soil. Okay, so in the case of your dense sand or in the case of your over consolidated soils, you will see how your shear stress curve is varying with the amount of shearing that you are trying to cause in your soil. And whereas your pattern of second curve, whatever you have seen, is generally what we come across in the case of your loose sand, or we say in the case of normally consolidated soils. Okay, so in the case of loose sand deposits or in the case of normally consolidated clay soil deposits. So in such case, if you are plotting a curve for that particular soil in which you have conducted your direct shear test, you would come across with tau versus displacement, shear displacement graph would be coming like this, as like mentioned in case 2. Okay, so you have to understand, depending on the type of soil what I am looking at, the condition of the soil, what is used for carrying out the test in the lab. So you would have different pattern of the curve. Ultimately, whatever is the pattern of the curve, whether you have a peak value and then your shear stress value is decreasing, or whether your shear stress is continuously increasing and remaining constant, how you are getting the curve, it doesn't matter. Our ultimate objective is to understand how much is the maximum shear stress value that your soil has as a capability before it is said to be undergoing the failure. So what maximum shear stress that was getting developed along this failure plane before the soil is said to be undergoing the failure. Okay, so that maximum shear stress value, once I know, then for that corresponding applied normal stress, let's say sigma 1, what was the maximum shear stress at failure of the soil sample 1, what your material has resisted. Like for sample 2, I applied some normal stress sigma 2, the corresponding maximum shear stress that your soil could resist at failure is tau F2. And likewise for sample 3, applied normal stress is sigma 3, and the corresponding maximum shear stress that the soil could have resisted before it is said to be undergoing the failure in case of sample 3, tau F3. So once these 3 points are known, try to join them by a possible best fitting straight line. Extend this line wherever it intersects your vertical axis, we represent it as your cohesion, and the slope of this curve is what we are writing it as your angle of shearing resistance, and this straight line is what we are calling it as your failure envelope. So ultimately, once I know my failure envelope, from that failure envelope, I am able to get what is your C and phi parameters of that particular soil, which I have used in the direct shear test. So if that's what I have been talking about, if from your direct shear test data, that is for the horizontal displacement data, what is measured from the dial gauge placed in the horizontal direction, which is giving you what is called as your, which we are calling it as the shear displacement, and the shear stress data, what we are simultaneously getting. If we are plotting a graph, I said in the case of your loose sand or normally consolidated clay, the pattern of the curve you will be getting it like this, as like what is mentioned in blue color. And in the case of dense sand or over consolidated clay, what you would see is that for lesser amount of displacement itself, you are going to see maximum shear stresses would get developed at your failure. And then if you are furthermore causing the shearing in the soil, you would see the capability of the amount of frictional resistance getting developed at the surface of contact slowly starts coming down. Okay, that is in the case of your dense sand or over consolidated clays. In such kind of soils, you will be having the curve like this. So ultimately, how is the pattern of the curve? It doesn't matter to us. What we are required to get from that, or what we are required to collect from that curve is what was your maximum shear stress that your soil could have resisted before it is said to be undergoing the failure. So pick that value, go on to plot your graph for sample 1, sample 2, and sample 3 test data, and you'll be getting your failure envelope. Once you get the failure envelope, from the failure envelope, you can determine your C5 parameters of that particular soil.